Hello and welcome everyone. My name is Dane Menke. I am the Digital Marketing Manager here at Regenesis and Land Science. Before we get started, I have just a few administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please try refreshing your browser. If that does not fix the issue, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we don't address your question within the time permitting, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's presentation will discuss a business case for achieving significant cost savings using colloidal activated carbon. With that, I'd like to introduce our presenters for today. We're pleased to have with us Jim Roll, Director of Environmental Services at WCEC. Jim Roll has 23 years of experience managing and conducting all aspects of environmental investigation and remediation projects in Montana, Idaho, and Washington, ranging from petroleum leak site investigations to complex fractured bedrock plume modeling and remediation. In addition to managing the nationwide operational, business, and financial aspects of the Environmental Services Division at WCEC, he advises and oversees project managers, engineers, and other technical staff as they conduct environmental site assessments and investigations, UST and AST removals, and remediation of contaminated soil and groundwater. We're also pleased to have with us today Todd Harrington, Global PetroFix Product Manager for Regenesis. Todd directs the expansion of the hydrocarbon treatment line in the global marketplace and provides industry-leading support to Regenesis customers. He has over 25 years of environmental remediation experience, primarily focused on in-situ remediation. He has been involved with thousands of contaminated site remediation projects during his tenure at Regenesis and has expertise with enhanced bioremediation, chemical oxidation, chemical reduction, and carbon sorption. All right, that concludes our introduction. So now I will hand things over to Jim Roll to get us started.
Thanks again, everyone, for joining us today. My name is Jim Roll. I'm the Director of Environmental Services for WCEC, and I'm based out of Missoula, Montana. Today, we're going to cover some considerations for design and implementation of remedial injections at petroleum cleanup sites. In this presentation, instead of focusing on the really technical specifics of how these various technologies work, this presentation is structured as more of a user's guide for consultants and regulators when designing and implementing remedial injection strategies. We're also going to look at development of the business case approach for remedial injections versus long-term monitoring costs. And that's as a component of a case study on a petroleum cleanup site in Washington State. And then we've got another case study that we'll look at that is a cleanup site in Polson, Montana, where we use the PetroFix reactive barrier to control a dissolved phase plume migration to a sensitive receptor. So with that, we're just going to cover a quick introduction, when to use in-situ remedial technologies, some of the common product types, groups, families, some design considerations when you're looking at implementing in-situ remedial injections, a bunch of common pitfalls and lessons we've learned in our days as both a remediation design consultant and also a remediation contractor, and then move into those case studies. So why would we use in-situ remedial technologies at a site? A lot of our sites nowadays are legacy cleanup sites, and they're at a stage where source removal has been completed to the extent possible, but there's some sort of lingering concentrations in soil and groundwater that are preventing regulatory closure. And the application of an in-situ remediation fluid, like we're looking at today, is an appealing option in these cases where a phase change technology like soil vapor extraction has not been complete, or there's other not implementable remedial strategies, or where natural or enhanced biodegradation are not effectively reducing concentrations in a reasonable time frame. So the primary focus of this presentation, one of the primary focuses is to unpack the most common pitfalls associated with application of in-situ remedial products and equip consultants and regulators with a set of best practices for design and implementation. Where and when would we use in-situ remediation? Remedial excavation, post-excavation, mixing of the product into the smear zone is really common. Smear zone injection is one of the most common application techniques, and we'll be looking at that today. Areas that are inaccessible for other forms of remediation are strong candidates for in-situ remediation. Great for dissolved phase plume mitigation, and then some more modern approaches, reactive barriers to control a plume, and then also even in emergency response situations. The most common application methods, like we talked about, soil mixing at the base of an excavation, trench installations, soil boring injections, which are the primary application method we're going to look at today, and then via injection wells. As an overview, we're going to break our remediation products into three families or groups. We've got your oxidants for in-situ chemical oxidation or ISCO, and then oxygen enhancement or enhanced bio, and then the activated carbon solutions, of which PetroFix falls into that category. So briefly, ISCO is direct oxidation of contaminants with reaction endpoints of carbon dioxide and water. Direct contact with the contaminant is key with ISCO. Multiple applications are commonly required if you're treating a source area with ISCO. And a couple of the downsides of ISCO, it can be unpleasant to work with in shallow applications. There is a risk to workers, they got to wear the proper PPE, and it can damage equipment and utilities. Now the upsides are ISCO is one of the injectables that it really is appropriate for treating source area with. The oxygen and nutrient enhancement products, these work with and enhance natural in-situ processes of biodegradation that are already occurring at a site. The microorganisms, in this case, convert the contaminants to those endpoints of CO2 and H2O. Delivery of oxygen is considered to be the most effective for the biodegradation of petroleum. And then other nutrients add terminal electron acceptors to the subsurface to help that treatment train along. This slide is just kind of an idealized redox zone within and surrounding a contaminant plume, in this case, the petroleum plume. And in general, enhanced bioproducts, again, they just augment these processes that are already occurring to reduce contaminant mass over time. Onto the activated carbon solutions. Activated carbon solutions work based on a combination of absorption and degradation. In essence, these AC solutions become part of the subsurface soil matrix after injection. The contaminants absorb onto the carbon substrate upon contact, and then a diffusion occurs as a result of a concentration gradient from high to low from source areas through the transport zones. Once absorbed, the contaminants are comparatively more available for biological and biochemical degradation. Most activated carbon products include a biostimulating nutrient blend to enhance those degradation pathways, similar to what we just looked at in the enhanced bio. The AC solutions, activated carbon solutions, fall into two general groups as we define here. You got your granular and powder activated carbons. Those are a larger grain size, typically injected at a higher pressure, 300 to 1,000 psi. And those higher pressure injections create or expand a higher permeability transport zone in tighter formations. The colloidal activated carbon, such as PetroFix, is a lower pressure injection, 30 to 50 psi, and those lower pressure injections effectively distribute the carbon across existing flux zones. So the next slide we'll look at shows you kind of an idealized picture of these two injection types and product types. On the left, you've got your granular and powder activated carbons, high pressure injection into a tight formation. And you can see there's kind of some microfracturing occurring, creating that flux zone. On the right, you've got the colloidal activated carbon. In this case, the injection into the sand layer within this clay matrix, you're filling that sand layer with the activated carbon. The key concept here is with injectable activated carbon solutions is that they function by controlling contaminant mass flux through the transport zone. So they're not going to effectively be distributed in the clay storage zone, but they are going to control diffusion from the clay to the sand layer, the transport zone, and groundwater. And then again, if sufficient carbon is present in the transport zone, the contaminants are effectively contained before they move off to a receptor. This is a geoprobe sleeve you can see from one of our sites that we're going to look at in the second case study. This is the transport zone that is filled with PetroFix in this case. It's a sandy gravel transport zone and an overall silty clay matrix. So just a quick summary, products that we just looked at, the in-situ remediation. You got your product groups on the left side and then kind of your site conditions across the top. You can see that the sweet spot for these technologies is really that smear zone and dissolve phase plume, appropriate for remediation when you have smear zone dissolve phase plume issues that you want to remediate. And then also as a reactive barrier. The ISCO itself, not really recommended for the reactive barrier. ISCO injections commonly result in desorption of contaminants from the soil matrix into groundwater. So you can mobilize some contaminants down gradient. We'll look at that a little bit more in the case study. And then again, with LNAPL present, this would be mobile LNAPL or high concentrations, not your low residual LNAPL. None of these products are really recommended if you have a high volume of LNAPL present at your site. Briefly, we'll look at the injection application methods. This is the primary mechanism application we're looking at with our case studies, and really falls into two categories here. You got grid injections and barrier injections. The grid injections, really common. This is a grid from one of our sites in the case study. You can see we've got a borehole layout. And then the key with grid injections is you're looking for overlapping zones of injection. So pretty self-explanatory, the good versus the bad here. You've got overlapping zones of influence here of direct injection. And then in this scenario, you'd have these gaps of untreated area. And we'll talk a little bit more about that later. In a barrier injection, this is a figure provided by Regenesis. You can see you have a groundwater plume and groundwater flow to the right. And here's your injected activated carbon barrier. And as contaminants move in groundwater through the barrier, they're sorbed and clean groundwater comes out the other side. And in this, you can see you may install multiple barriers along the flow path of a plume to achieve your remediation goals. So some key concepts when it comes to remedial design, and we're going to hammer on the conceptual site model a lot. A lot of these, any remedial strategy really comes down to how robust your conceptual site model is, how good is your understanding of your site, where are your contaminants, what kind of hydrogeology do you have, what kind of lithology do you have, what are your storage zones, and what are your flux zones. Those are the things you need to know to design a robust and appropriate injectable remedial strategy. We like to look at individual treatment areas versus the whole site. This is a key concept. The whole site's not created equal. There's different concentrations. There may be different subsurface conditions. You may have an old excavation footprint that's going to be able to receive an injection at a higher rate or a higher volume than unexcavated areas. Those are really the conditions you need to look at when you start working towards a remedial design that includes injection. Again, the business case approach we'll look at in detail, and that really is focusing on what cost does the remediation save in the form of long-term monitoring, particularly at the end of a project life cycle if you're talking about a multi-decade long-term monitoring program. Another key concept is to continuously revise and refine your remedial process, including your conceptual site model and your design. Everything you learn about a site as you move on informs the next decision. And then a pre and post remediation monitoring strategy is also key to prove what you've done was effective. So some keys to successful in situ injection, I call this the 4Ds. Detailed CSM is number one. You're going to hear that a lot today. A robust design that's based on the CSM, having adequate dosage, and then successful delivery of that dosage to the target zone. So look at the conceptual site model development briefly. You want to know your contaminant distribution concentration, again, subsurface geology, ID those storage and transport zones, have a good idea of your hydrogeology. Today, we're using a lot of the high resolution site characterization or HRSC tools. That includes UVOST LIF, electroconductivity, a bunch of these in situ tools that really can show you your contaminant mass and distribution in real time. and then use that CSM to calculate a restoration time frame using a first order decay rate. We'll look at that in the case study a little bit more as well. And you can see this is a picture of one of our sites in eastern Montana, UVOST, LAF, and EC, and you can see we've got a really good handle on the spatial distribution and concentrations of the contaminant mass at this site. Product selection for your site, again, totally guided by the CSM. You need to have a good CSM to select the correct product for your site. You're going to work with the product vendors. These product vendors have a really good idea how their products work, and they want their products to be successful. They're going to work with you to help you select the right product and the right design. And as some questions you want to ask yourself when you're looking at in-situ remediation, do you have a lot of LNAPL? What are the receptors? Are there third parties? Logistics and access, is this an implementable strategy at your site? You might consider multiple products to achieve remedial objectives like ISCO in the source area and a reactive barrier with PetroFix downgrading to control that desorbed groundwater plume that may be released during your ISCO injection. And then also consider a pilot study to help reduce the number of unknowns in your full-scale design. Let's look at the dosage calculation a little bit. Again, CSM, I said we're going to hammer on it, but the better your conceptual site model is, the better idea you're going to have about what dosage is really required to remediate your site. Again, work with the product vendors. Regenesis has advanced tools for calculating dosage. They want to help you get the dosage right for your site, and they do this every day. They can help you figure that out. Evaluate your individual treatment areas. So you can see in this site, we've got a source area remedial injection and then a downgradient smear zone. There's different concentrations in those two areas, different subsurface conditions, and our design took those into account to make sure we weren't underdosing or potentially overdosing an area at the site. So in the implementation phase, some of the planning considerations, you're going to need a water source. That's a big deal on these projects, not always easy to find. You're going to need a mixing area, and the mixing area, can be messy. You want to think that through before you make a big mess at your client's site. And you can see in this picture, this is an ISCO injection where we had high groundwater and there were somewhat shallow injections and we had some surfacing and it was messy. And that also speaks to timing here. We probably should have waited to do this injection during low groundwater, but we all know, there's regulatory oversight and our client were pushing to get this work done, did it during high water, and you can see that we had a mess here to deal with after we did our injection. So pick the ideal time to do your injections at your site and make sure your client's on board and the regulators understand that having the right conditions is key to delivering your remediation product into the correct area of your site. Then the final piece of remediation design, follow-up monitoring. This is a big deal. You got to prove that what you did was effective. We like to conduct an initial event within about 90 days, and then at least a year of duration of monitoring after an injection event. And then a big point here, always use unbiased monitoring points. Don't sample wells that were used as injection points, for example. Maybe give those a year, redevelop them before you're going to use any sort of injection well as a monitoring point. And then be prepared for, some mixed results when you're doing your post-injection monitoring. It's not uncommon with ISCO at all to see an initial increase in dissolved concentrations and potentially an initial increase in the extent of the dissolved phase plume, the spatial extent, from the desorption of those constituents from the soil and the groundwater. And then with the carbon products, be prepared to see an initial decrease in concentrations in the injection area followed by a rebound. And that rebound likely to occur if you have some underdosing or ineffective delivery to your target zones. Now let's look at a couple common pitfalls in the design process. And these seem really straight ahead, but does your design actually work with site conditions? This is a trap that folks fall into. You have a desired remediation product and approach, and it just isn't right for the site. Make sure that you consider that there's an application reality. Is your injection strategy implementable at your site? And again, listen to the product vendors and the application contractors, the folks who do this every day, work with the realities of injecting product into the subsurface. Few application pitfalls when you're out there actually doing your work. Again, seems super simple, sometimes harder to achieve than it would seem. You got to place the product where it needs to go to ensure contact with the treatment horizon. Don't count on any distribution through natural processes. Groundwater is not going to take the product you inject and distribute it evenly to all the zones that you would like to treat. You have to put it there via injection, use an overlapping grid design, use field assessment for distribution. You can see in this slide, this is a varve lake bed sediment. We got some secondary porosity features in this case that are occupied with PetroFix. So we know that we have good distribution through those transport zones. Keep an eye on system overload, too much volume, too high a pressure, too fast a flow rate. Those can lead to surfacing, and then make adjustments in the field. If things aren't going the way you think they are, and they're probably not going to go exactly how you drew it up, make adjustments in the field to make sure that you're delivering the appropriate volume and concentration of remediation fluid to the correct zone that you're trying to treat. Underdosing is a big pitfall, most of the time due to an incomplete CSM, but also I use this term administrative underdosing, which is a common problem. And that's just the world we operate in, where the science alone doesn't determine the cleanup strategy. And there's a lot of pressure on these sites. There's financial pressure, there's regulatory pressure. People don't understand the technologies as well as you do. And these can result in arbitrary changes to the design in a review phase. Communication with your stakeholders is key to help them understand why these changes will result in ineffective remediation and ultimately increase long-term costs for the cleanup. So for us, one of the best ways to preemptively strike against these administrative underdosings is by development of a business case approach. A typical business case approach compares the cost benefit of conducting effective remediation versus achieving closure with modern natural attenuation long-term monitoring. Again, it's going to be based on that CSM. The big piece here is the restoration time frame using a first order decay rate with a 90% confidence interval. I have a reference on my last slide that is from the EPA guidance on calculation and use of a first order decay rate constants. That's a commonly accepted technique, really defensible, and that's what we use for our restoration timeframes. And then in the context of your regulatory requirements, how much monitoring do you have to do if you're going to go for M&A as annual, quarterly? Depends on the state, depends on the regulatory body. And then use that restoration time frame and those requirements in conjunction to come up with a cost to closure. I don't have to remind anybody that inflation happens. We use 2.5% in this case study we're going to look at. It could be a lot higher than that, like it was the last year. And then look at a break-even analysis. Again, that's how much does the remediation cost in the context of years of monitoring saved at the end of the project life cycle. So with that, we're going to jump into this first case study. This is a map of that site. It's a former retail fueling station with USTs. You get the USTs here and the pump island here. And there was a release of 2,000 gallons of gasoline in 1997 from the piping from the tanks to the pump island. That's when we got involved. Project started with a remedial excavation and a recovery trench, product recovery, and that was in 97, then followed by a limited RI. In those days, the RIs were really limited compared to what we do nowadays. We had 8 or 10 borings and then 3 monitoring wells, 1, 2, and 3. Monitoring well 2 is kind of a source area well, and then 3 was considered our proximal down gradient well. 1 was an up gradient control well that really tailed off pretty quick after the excavation. Quick rundown of the CSM here. Subsurface was a homogeneous silt. Groundwater is present 6 to 8 feet. Groundwater flows to the southwest, and then we had ongoing BTEX impacts to groundwater post-excavation. So we did a few more years of monitoring and then looked at some remedial technologies and landed on a combined ISCO oxygen enhancement injection. We did a pilot study around MW3, just a small scale injection. That had promising results, so we moved to what we considered a full scale design at the time, same product that we implemented in 2004. That injection event was really successful. Here's the grid. You can see it was super successful in reducing BTEX concentrations in the source area. You can see we've got the next slide. This is benzene concentration versus time in MW3. Vertical blue line signifies that ISCO oxygen enhancement. And you can see we had really good results reducing benzene at MW3 from that event. Speaking of the ISCO and desorption of contaminants, what we didn't expect, same blue line signifying the injection event. In the source area, we had an increase in MTBE after the ISCO oxygen enhancement. So this was something we didn't expect to happen. That happens in remediation. That's why you do post-injection monitoring. So we were left scratching our heads a little bit about this. And if we look at MW3, it's really evident we had MTBE increase, and this is a downgrade, well, increase in MW3 over time. So we went back, did some more monitoring, scratched our heads a little bit, and started working on a restoration time frame to work towards a business case, remedial strategy, and cost of closure. So really here you can see we have this huge increasing trend, not much of a declining trend, and then the first order decay rate range pretty wide, and we used the midpoint of the decay range, which put us at about 40 years for monitored natural attenuation. And that was from 2013 is when we started this business case approach. From there, we went into a cost of closure. There was a limited amount of insurance funding available for our client for this release. I wanted to see if we were just to do long-term monitoring, if those funds would be adequate for the cleanup, or if we could do remediation and reduce their overall costs. Again, we use that 2.5% inflation, and then we included a break-even analysis for the cost of the remediation compared to elimination of some of those later years of long-term monitoring. So here's our business case we put together in 2013. We were running about a burn rate of about 20,000 a year in Washington. Standard issue regulatory requirement is quarterly groundwater monitoring until you achieve 8 consecutive clean quarters. And you can see we have our 20,000 base price in 2013, 2.5% inflation. This is just doing long-term monitoring, no active remediation. I cut out about the middle 20 years here, and you can see end of life cycle, you're pushing 50K a year for quarterly groundwater monitoring, and to the tune of about 1.25 million to close this site via M&A projected. So that's a pretty huge price tag. This was going to exceed the policy limits for our client. So we worked with a remedial strategy. Again, this is that break-even analysis. Our remedial strategy was about 150,000 for the injection event. So if we were able to save, 3 years of monitoring at the end of the project life cycle, that would pay for the remediation of 150,000. It's a strong business case to our client and their insurance company, and they said, yeah, let's do it. Let's get into some remediation. The next phase of design was an ORC application, and this was in 2013. You can see a much more robust injection grid that we used. We had a better CSM. We knew we needed to cover more area. And this 2013 injection strategy, this is MTBE, our problem child, is the only contaminant that was above Motka methadase standards. You can see here's this purple vertical line is the ORC application 2013, and really effective in mitigating MTBE. This would be in the source area, and we had it below standards within a few years. And then that down gradient well, the proximal down gradient well, MW3, again, the vertical purple line is the ORC injection, and we've got a great degradation curve here. It monitored for a few years, and then things were looking good. Didn't think we're going to need to do more remediation. Again, first order decay rate, we were looking at a projected timeline of about, from that time, 2019 and about 2023, we'd hit cleanup standards and get this site closed with just M&A. At the time, 2019, the case manager Department of Ecology in Washington, we had a new case manager, and that happens. You get a new case manager on a site. Sometimes you get 3 new case managers on the lifetime of a site. And we asked them, hey, looking towards closure here, what else might we need to do? What do you want to see to get this thing to closure? They said, let's do some off-site investigation in the alleyway to the south. And a typical site and client, we hadn't investigated this roadway because it hadn't been required by the regulatory agency. Not uncommon in the era that we were working on this site early. And we went ahead with that investigation. Sure enough, this well MW5 down gradient of our treatment area had the highest MTBE concentration we'd seen in site history. So we knew we needed to do some more cleanup and went back to the CSM, back to the design wheel, looked at cost of closure again. And this time we talked to a few product vendors and landed on PetroFix as a remedial solution, and we're worked toward the design in 2020. Again, updated the cost of closure. You can see here, we got a $52,000 injection event. And then what we thought based on site history, we might need, 3 years of events quarterly to get us towards closure for a total of 178,000. Still looking okay on the insurance money. Insurance company and the client said, let's get this done. This time our design, we used the PetroFix online design assistant, 3 injection areas, 3 distinct design areas, different concentrations, different subsurface conditions in each area. You can see there, each had its own injection volume. And this injection event encompassed, the historic source area and some residual areas, that east area, and then that down gradient area in the alley. So we injected in 2020, that's this vertical yellow line you can see, and the PetroFix really wiped out the MTBE. This is an MW3. We were getting close, and you can see it just drastically reduced concentration. So we did have a little rebound, not uncommon, but still well below that cleanup standard of 20 micrograms per liter. And we stayed there for 3 years. So this site's looking towards closure. MW5, that down gradient well in the alley, again, the vertical yellow line is the PetroFix injection, and again, reduced concentrations to non-detect within about a year, and then a slight rebound, but still maintained concentrations below that cleanup standard. So we're looking at closure. This site is actually in review for closure by ecology based on these data. So you're saying, what, we did a lot of work out there. What actually happened with this business case? So this is our running actual cost from 2013 through 2023, annual costs in this column, and then the running total here. You can see 2013, we did the first injection event and some monitoring, some more monitoring into a remedial design, and another remedial injection in 2018, some more design and monitoring, and then into that PetroFix injection in 2020. And that puts us at about $500,000 cost of closure. And remember, we were looking at 1.25 million projected M&A versus that $500,000 actual to get this thing to closure. That's a cost savings of $750,000 and within our client's insurance coverage. Lessons learned from this project. Of course, if we would have had a complete RI and a comprehensive CSM early in the project life cycle, it would have helped us out a lot. We wouldn't have had those multiple injection events, and it would have even further reduced the duration and total cost of cleanup. The resulting design would have been a little different. Knowing what we know now with 2020 hindsight, 2 treatment areas would have been ideal here with a pre-installed PetroFix barrier. So the blue there, we would actually install that PetroFix barrier before completing ISCO in the source area, and that barrier would have helped us control those offsite migration of MTBE in this case, desorbed from the source area. So treat the source area with ISCO here, and then you have that pre-installed barrier to prevent offsite migration, this plume migration that we created with some of our injection events. So our second case study, this one really is focused on the reactive barrier approach, and as a good lead in from that last slide with the lesson we learned there about a reactive barrier. This site is in Polson, Montana, and the strategy here wasn't remediation of the source area. Is a large scale site. The injection strategy was to control migration of dissolved phase constituents to the sensitive receptor, in this case being Flathead Lake. This is an old site, initial investigation in the 90s. Tanks date back to the 50s. 13 different PRP ownerships, and there's a large undefined El Napo plume here. Is actually, when we defined it, it's a 3-acre El Napo plume under downtown Polson. El Napo thicknesses and monitoring wells across the site. There's a complex lithology. Here's a glacial lakes. You have varved lake bed sediments, secondary porosity features, desiccation cracks filled with sand, things like that. It's complicated. It took us a while to understand it. HRSC tools were huge here for us to understand this site. And then, of course, you have the sensitive surface water receptor in Flathead Lake and a complex regulatory climate with DEQ, the city, the county. This Polson is on the Confederated Salish Kootenai Reservation, so we have the tribe and the US EPA involved in this site. Again, we went right into the CSM development. Our HRSC investigation area, you can see in this slide, encompasses a lot of downtown Polson. This is Flathead Lake, and the epicenter of this release site is in this area, which is called the Four Corners. There's a Four Corners in every town, I think. We conducted a UVOST LAF investigation, HRSC investigation, included the EC. It was structured to identify the 3-dimensional extent and magnitude of the El Napo plume, and then also those primary mechanisms that dictated El Napo distribution and transport at the site. So this is a resulting 2-dimensional El Napo body. You can see the high concentration areas and then migration of, this is still mobile El Napo at this time, down to the lake. This is a perspective view of the 3D El Napo plume underlying downtown Polson, which sits here. What we also found using the HRSC tools and some elevation data is that the maximum extent of vertical migration was dictated by the high pool and low pool level of Flathead Lake, natural lake, but dam controlled, and that influenced our El Napo distribution vertically. From there, we went into some targeted remediation, extraction wells in the high concentration areas, and then also product recovery and groundwater monitoring. The product recovery was relatively effective in reducing the footprint and extent of the El Napo accumulations. We had this big dissolve phase plume that we're contending with at the same time. You can see that here. This is benzene and groundwater in 2018. This is actually a separate release site that we're working on. There was some commingling at the time, but this is the primary resulting dissolve phase plume from this Four Corners site. You see it's migrated down towards the lakeshore, and we've got a line of wells along the lakeshore, dissolved concentrations at the lakeshore exceeding standards. We worked with DEQ. This is a primary concern, was to mitigate any discharge of dissolved phase contaminants into the lake. So we worked with Regenesis and DEQ and came up with a PetroFix reactive barrier approach to limit any migration of contaminants from that plume into the lake. The reactive barrier consisted of these tightly clustered injection borings with a target injection depth that corresponded with a transmissive transport zone that we'd identified during the HRSC investigation within that overall lake bed sediment matrix. Again, this is a slide we saw before, but this is from our injection in that reactive barrier. Again, you've got that transport zone, sand and gravel. It's completely occupied with PetroFix here. And this was during injection to make sure we were getting the distribution that we wanted into that transport zone. And then this relatively, impermeable or much less transmissive silts and clays. And so it was a really effective injection strategy. You can see our next monitoring event, the plume. We've also done some El Napo recovery here. This is slightly less intense, but we've totally disconnected the plume from the lakeshore. You can see with all this monitoring data. So again, I'll just flip back and forth between the pre and post just for kind of the visual of the effectiveness of this reactive barrier. So you've got pre-injection, dissolve phase concentrations get into the lake, and then post. So pre and post, really obvious it was effective for us. So with that, I'm going to reference this slide, and I'm going to pass this off to Todd for his portion of the presentation. Thank you.
All right, Jim, that was an excellent presentation, a lot of great material, pretty exciting stuff. As I thought about how to transition into some supportive information for this, I thought it would be appropriate to focus on, how we work together to design and apply PetroFix, the supporting materials around our customers, the same stuff that we work with Jim on to get the success he did. So I'm going to focus on how we support you to achieve remediation results. To just kind of recap what PetroFix is, just one quick slide. It is a colloidal carbon. Jim was showing the material going through the flux zones, and it's designed to do that under low pressure. So it ships out as a suspended colloid of activated carbon that's actually diluted in a mixed tank and filled. And in that mixed tank, we add soluble sulfate and nitrate salts for the electron acceptor. So it's a 1-2 approach. And then you can take that remedial fluid and then you can inject it like he did in barriers or grids or other innovative applications like inland spill response or tank basin flooding and corridor flooding, that nature. So lots of creative type things that you can do. So this product's been out for 4.5 years roughly, and I've been at the head of that for nearly the entire amount. And so today we have about 811 projects worldwide in 42 states and 18 countries. And that's fun to brag about. I think there's been a lot of growth, but really the point I want to make is we've learned a lot. And what we're taking here is we're taking a colloidal carbon that has some specific ways that are not all that hard, but some specific ways to make sure that it gets distributed in the field appropriately. And I'm going to get into the online software a bit that Jim mentioned, but there needs to be surrounding ecosystem of support to make sure that you do it well. And we have tried really hard. In fact, I think this may be the most supported in-situ remediation product in the industry to give you the information that you need to get it into the ground and distributed. So that includes a variety of things such as application instructions, product literature along the lines of spec sheets and menu brochures, SDS sheets as you would expect, design tools, and lots of technical bulletins on how to sample groundwater, how to handle the material, et cetera. It's there for you, and I highly recommend that you take a look at this information as you proceed towards a PetroFix application, or call us up, as I'll get into, and have us interact on your site, and we can help you along with that. But we do have 19 case studies, and Jim's is one of those, and lots of great stuff there. The support does start, and I recognize I'm referring back to Jim's talk quite a bit, but having a good remedial conceptual site model. So take that data from your conceptual site model, and you have the option to interact and do a PetroFix design first, either online, free online software, or Regenesis can do offline designs, and I'll get into that more. But it funnels you through a lot of design safety rails that we do have warnings and red flags, and so we feel comfortable enough to put this online. And if you adhere to that, you're going to get a good injection, and so that helps eliminate a lot of doubt for that. But on top of that, we do have this large support library that really helps you prepare, inject, verify distribution and sample, things that are critical to the success of your job. And cradle to grave support here means that we are here ahead of the project, helping you prepare for an application. We're here if you're in the field or for post data review. And we've spent a lot of time with Jim actually on this. I would say Jim's a pro right now. So a lot of the stuff that I'm talking about today, we've gone over, but he's quite expert at this point. In terms of the design assistance option 1, you are more than welcome to try out our online software to come up with a PetroFix design. If you go to petrofix.com, or you can even find it at regenesis.com there. And you're going to find that you can do the typical approaches. You're going to run into a grid design, you can do online, an excavation design. Barrier designs are still offline at this point. There are complexities there, and so we feel more comfortable doing those for you. At the date of this webinar, we've had a series of 3 webinars by Dr. Jeremy Bernstengel on Plume Force, a modeling software that we use. We actually use that same software for the hydrocarbon sites just to make sure that we're dosing appropriately. So a lot of design safety involved with that, a lot of support around it. And I think the best thing that I can do is to show you one of the pages there and kind of dig into the software a little bit and some of the features you may not be aware of. So this is a typical design that I did, saying 3,600 pounds for this particular 2,500 square foot site. One of the great things about the software is, depending on the scale of the site, you do probably want to break things apart. slice and dice so you have really good optimized design. There is live chat support through most of the day, so if you have any questions, please ping us. Tyler Harris or myself or another design support specialist will be there to answer any questions, even do a desktop share with you. You can get your price estimates. You can actually come back when you get approval and order directly from the website, and then Regenesis will take that information and coordinate shipping for you. And we also have hot link checklists, and these are important because it's not just coming up with a good design, but just making sure that you inject it with the right tooling, that you adapt in the field, and you have the knowledge to do so. So we've put into checklist form a lot of the most critical documents out of those 20 documents we talked about at different stages of your project. There's certain things you need to think about before you do an application, perhaps during an application, you know, the tools, pumps, etc. Or after an application, how do you monitor groundwater? What should you be measuring for groundwater? All this has been put together in this extensive library to help guide you through these phases. I'll come back to that in a little bit, but I want to transition into the other option to get a design is really just to have Regenesis do it. That's how many of you are probably familiar with working with us. In the past, so PetroFix is a bit of a new experience that we've done in the past 4.5 years. But why would people come to us this way? It could be a complex or unique site. There's specific logistic issues, challenging injection, maybe a large site. It can be debated on what a large site is. We're thinking that maybe anything bigger than 2,500 square feet or 10,000 pounds. It really just depends on your level of experience, but we're there for you if you want us to just take a look and if we can think of a better way to approach what you're up against. So if there's any uncertainty or you just desire support in any way, we're there for you for that. One of the things we also do, which I think is really important, and most everybody is not aware of this, particularly for people who are just getting into their first or second PetroFix project, is that I or Tyler or other tech services people will coordinate free pre-application calls. So what you don't want to do is show up on site and your injection contractor might be missing the wrong transfer pump or not able to mix the product appropriately or possibly have the wrong tooling for the geology. The stuff that you need is not that hard to get. It's pretty common, but it's good to get on the same page to review that design. So we do that for free if you want, and we usually try to do it 2 to 3 weeks ahead of an application to cover things. And then we review those injection best practices on how to mix tooling and how to sample. And it really catches a lot of things. So just keep that in mind if you're coming into this and you don't have a lot of experience. And one of the things that also was mentioned in Jim's part of the webinar, and we focus a lot on, and I'm just going to touch base on today, is that we have a lot of methodologies available to you to make sure that you can adapt in field and make sure that the material is going where it needs to go. You want to have overlapping radii. This is a cross section where the radii are not quite overlapping, and you can imagine how benzene might be able to squeak through to a monitoring well. With the right number of wells, the right number of temporary piezometers, you can measure distribution just by the color of the material and make real-time adjustments in the field by making adaptive adjustments. Very important to consider, and we're happy to talk about that. So all of this is in the pre-application call. We actually have a YouTube video that you can go to if you type up PetroFix pre-application presentation. A lot of the material there is just discussed if you choose to go that route. And then finally, for my last slide before some Q&A is probably less than 10% of the sites, people for large complex sites often want to have Regenesis turnkey. We can do that. Is self-design and self-apply as this technology is, that is available to you. Our crews have great efficiency and the best safety operating procedures, state-of-the-art equipment. Our crews can adapt. They know how our products work in the field, the tooling to use. Many of our crews are four-year college degree, so they can consult with you and give you the next steps and make sure you're getting that distribution. So that is definitely an option for you. But with that, let's stop there. And Dane, I'll turn it over to you, and why don't we get into some Q&A?
All right, thank you very much, Todd. So yes, as Todd mentioned, that concludes the formal section of our presentation. So at this point, we would like to shift into the question and answer portion of the webcast. All right, so let's circle back to the questions here. This is a question for Jim. Jim, the question is, what kind of geoprobe and tools did you use?
Yeah, thanks. Typically, we use a geoprobe 7822 DT, which is a larger geoprobe tracked rig that has the power for us for the geology, particularly out west, to get to our target depths. And then a track rig lets us get around into some tight spaces. So we've used a lot of geoprobes over the days. Depending on the lithology, you can go smaller, but that 7822 is kind of our go-to machine for injection work.
All right, thanks, Jim. So this is another question. It could be either for Jim or Todd, and it is, you injected PetroFix near the water in the last case study. Did you have issues with PetroFix impacting the surface water?
Yeah, I can take that one first. Yeah, we didn't have any PetroFix show up in the surface water there. We injected actually that, like I said before, that natural lake dam controlled nowadays, and we selectively injected during a lower pool condition to mitigate any risks that we may have had. Definitely wasn't the design to inject until we saw it in the lake, and it didn't occur there, but something you want to be cognizant of when you're injecting near a receptor, with PetroFix or any other injectable for that matter.
I'll add to that a little bit to what Jim said, and we agree. I mean, we are aware that most aquifers don't travel so quickly that they're going to pull things in. Often it might be some sort of utility that we might be concerned about, but we take that into account. Typically, we'll tighten spacing, lower volumes, and try to stay plenty of distance away. There's all the other ways that we can help people. It's possible to inject accompanying geochemistry, divalent cation chemistry that can help accelerate the stabilization of the colloidal material. We call it parking, so it's actually possible to do that. So keep that in mind if you have that. We always look to possibly use that approach as well.
All right, so here's another question. This one is for Todd. Todd, the question is, can you inject PetroFix in clay?
Yeah, it's a good question. So, you run into that with mixed geology. So the technology, we are going for a low pressure, typically 30 to PSI delivery. And so we don't inject into clay. So to answer that directly, we're not trying to fracture to getting into clay. Groundwater plumes are not migrating through tight clay, but what they're migrating through is the sandier, more permeable seams that Jim actually showed a picture of that. So we do inject in the clay, but the focus is to try to get that lower pressure distribution through those particular flux zones. So that's typically what we're trying to do.
Okay, thanks, Todd. So here's another question for Jim. Jim, the question is, what did you find was the most successful way to inject the material at your sites?
Yeah, as far as tooling goes, we've used both pressure activated tips and the retractables. Both are appropriate. I'm not sure the total context of the question, I guess, but we typically we're working with a bottom-up injection technique. That's been the most implementable for us, and it's been pretty reliable. Drill to depth, to your first target depth, and then inject into those target depths as you move upward. And from there, it's really just injecting at the rate that the subsurface will accept the product. You could try to go too fast, you're going to get surfacing. And if you do get some surfacing, I would just say slow down, tighten up your grid. Maybe if you have some latitude to reduce the overall volume by increasing the concentration of PetroFix in the solution, go that route, and then just verify that you're getting the overlapping coverage that we showed some different slides of.
All right, thanks, Jim. So that is going to be the end of our chat questions. If we did not get to your question, someone will make an effort to follow up with you. If you'd like to learn more about services from WCEC, you can visit wcec.com. If you'd like to learn more about remediation solutions from Regenesis, please visit regenesis.com. Thanks again very much to Jim Roll and Todd Harrington. Thanks to everyone who could join us. Have a great day.